This is our first webinar, and that is sure, I think. We agreed about that. So after this introduction, you will have the possibility to listen to the presentation of Dr. Chris Robertson from Polymer Technology Service, LLC, United States. He will report about his chapter in the book I will present in the next slides. So you will see there also the title of the presentation in some more details. Then, after that presentation, Dr. P. Ghosh from Assoc from India will give a presentation about his chapter in this book. And then at the end, Mr. Professor Stocek from PRL, from Zlin, Tomasz Bada University, will present his results that were written down in the not only one chapter. He was here very active with delivering material that you can find in, I think, in 3 chapters in this book. At the end, I will give some closing remarks. And here, finally, you see the covers of the book about which we will report today. This is the book Fatigue, Crack, Grow in Rubber Materials that appeared 1 year ago. In this presentation that I think will also be distributed, you see also the links. And if you have time, you can then open these links and you can then see details about the contents of the books. You can read the introduction, etc., and so on. And if you are really big interested for many chapters, you can also order this book, or you can download this book in agreement with the publishing company Springer. It's a pleasure for me also to note that we have just recently published another book. It's a second book that is more focusing on degradation of elastomers in practice, experiments, and modeling. About this book, we will today not speak. And I also will like mention that a collection of some interesting papers dealing with advanced testing of soft polymer materials was just recently published in a book from the MDPI publishing company. It is a special issue of the journal, of the scientific journal Polymers, and it is dealing with several issues concerning new testing methods and advanced testing methods, especially for soft polymer materials, mainly rubbers. The book Project in Preparation that I will mention, as I said, is focused on advances in understanding thermal effects in rubber, experiments, modeling, and practical relevance. We hope that this book will be ready at the end of this year. Till now, we have 14 chapters, or we have asked 14 authors that agreed to report about latest results. You see here the keywords. I will not read all these in details, but you can see here within this book that is in preparation, self-heating, heat generation, heat diffusion, heat build-up, and so on will play a big role. Applications are tires, also presentation of new testing methods, and also news concerning the analytical modeling and also numerical simulation. More but not least, we can say multi-scale simulation of these temperature effects during crack propagation, during degradation, and so on. So last but not least, 2 books in these series are ready, are available. This book is in presentation, and another book gives an outlook about testing methods. What is now the main goal and the main content of the chapters in the book about we will report today? Fatigue, crack, grow in rubber materials. I have here that written in some brief sentences. It summarized the recent research and the experimental developments regarding fatigue crack-grow investigations of rubber materials. It shows the progress in fundamental as well as in advanced research of fracture investigation of rubber materials. It describes the progress in numerical modeling and also in physical description of fracture mechanics and also in cavitation phenomena in rubbers. It considers initiation and propagation of cracks in rubber materials as a dominant phenomena which determines the lifetime of rubber materials. It describes new experimental methods, concepts, and also models. Concepts means here also how to evaluate correctly the data. And also in some chapters you find explanations about crack phenomena and its impact on rubber wear and abrasion, especially of automotive tires. It's also an issue that has now a big importance now for many branches in industry, in rubber industry and tire industries. This is the content, and the green marked headlines are related to the presentations today. As I already mentioned, Stocek will give a presentation about some revisions of fatigue crack-grow characteristics and also some special issues concerning the determination of the parametrical functions, which define the deformations within a plane strain tensile rubber samples. So this is here focused on also discussing inaccuracies in fatigue crack-grow characteristics, and also it is focused on consequences on the development of durable rubber compounds. Chris Robertson as the next speaker, or as here in that case it is the first speaker, he will report about his chapter that is dealing with the fatigue threshold of rubbers and its characterization using the cutting method. So in this chapter you will learn more about the definition. What is fatigue threshold? What is endurance limits? And all these very specific but very important keywords in connection with the fatigue physics and the fatigue engineering of these materials. And last but not least, also in this chapter, you find a very nice review about the molecular interpretation of all these parameters. So in this book, you also find chapters from Will Mars, very known guy from the United States in this field. We are reporting he has written a chapter about critical plane analysis of rubber. We have also a chapter from Luxembourg about cavitation micromechanisms, especially in silica-filled styrene butadiene rubbers, about fatigue and cyclic testing. We have a chapter from Israel from Dr. Woloch about new approaches to modeling failure and fracture of rubber-like materials. This is a continuum mechanical approach that is presented there. Then from Hanover, from the Rubber Institute, we have a chapter about the influence of filler-induced cracks on the statistical lifetimes of rubbers. No? If you have a certain distribution of defects like fillers, how this distribution influences the initiation and then the propagation of cracks. Very interesting is also this chapter from Mr. Eberlein et al. About fatigue life analysis of elastomer-like polyurethanes. It's not the classical rubber we have here in mind, it is polyurethane. Then a chapter from Dresden, cavitation and rubber volcanizates subjected to constrained tensile deformation. Maybe this is also content of the next webinar. We will report more in detail about that. And then we have the presentation of Dr. Ghosh from Hasetri about fatigue crack growth and about the relationship and the impact on such phenomena like chip and cut wear. Here, especially chip and cut wear of natural rubber natural rubber systems and natural SBR blend systems. This is, of course, very interesting for people that use these kind of rubbers in connection with the production of tires. Last but not least, only to mention, it's not the topic today, but I would like to mention that here in my introduction are the other chapters that are still in this book. That is a review on the role of phase morphology and the energy dissipation around the crack tip during the propagation of cracks in a rubber system. That is from Hannover with Dr. Klippel and Mr. Wunder. And then also thermoplastic elastomers. It's not only an issue of rubbers, of classical rubbers. It's also an issue for people that are dealing with thermoplastic elastomer. And this is the contribution from Professor Mayo from Linz, from Austria. He presents here a methodology that is used for the characterization, the fracture and fatigue behavior of TBEs. Then we have a French contribution about the influence of materials parameters and the ultimate and fatigue properties of elastomers. That is also very interesting because you see here also a very nicely description of the connection between material parameters, for example, from dynamic mechanical characterization, and how these material parameters are connected also physically with parameters that describes the fracture mechanical behavior of these systems. So then we have also a contribution from Merseborg about the influence of plasticizers on the fracture behavior of elastomers. We have a presentation that describes the state of art of numerical simulation, computational mechanics. That is from Dresden, from the group of Professor Kaliske. He is presenting here the phase field method as a very powerful method for describing crack propagation, fatigue behavior of larger rubber parts. Then we have a chapter from Bo Persson and co-workers. Bo Persson is very well known in the field of rubber friction. Maybe you know that. This is here a chapter that gives a review about theories and applications related to the viscoelastic crack propagation. More or less a description of the relationship between the viscoelastic character of these materials and its influence on crack initiation and crack propagation. Last but not least, a chapter about dissipative heating, fatigue, and fracture under multi-axial loading. That is also from Dresden, from the Leibniz Institute of Polymer Materials. And at the end, we have a contribution from United Kingdom, from James Busfield and his co-workers about the determination of the loading mode dependence on the tearing energy and the fracture mechanical behavior, multi-axial deformations. And the French contribution, Constant and co-workers, is focused on the small X-ray scatter and wide crack tip and how this information can be used to understand better what really is the driving force, the driving mechanisms for the fatigue crack propagation. And here, especially in natural rubber, where also strain-induced crystallization plays a big role. You see here a sketch of the experimental setup and the scanned area that is a figure from this chapter. So this is the content that I have briefly explained. I think we can now start with the first presentation. And to everybody, I wish here a pleasant seminar, a pleasant webinar, better to say. Enjoy this webinar. Ask questions. If you have these questions, use the chat function again. You will receive an answer. We will also keep the contact to you. And I would be very happy together also with the co-authors of this book and also with all the authors of the chapters of this book, if you would also show interest then for the next webinar that we will then announce right in time. Thank you very much.
Okay, Chris, the stage is yours now.
So, ich bin wieder hier. Ist meine Präsentation weg?
Ja, ist weg.
Okay, thank you for the nice introduction. Hopefully you can see the slides. Is that right?
Yeah.
Yes, we can see.
Okay, very nice. As Professor Heinrich mentioned, we were privileged to be part of this book, and what I'd like to talk about today is the fatigue threshold. It's not as commonly understood by the general rubber community, so I'll spend some time explaining it. In particular, there's been a recent advancement in how to characterize this parameter using the cutting method, so there will be some focus on that. I would like to acknowledge my co-authors, Dr. Stocek from PRL and Dr. Will Mars from Endurica. I spent 4 years working at Endurica, and just over a year ago, I decided to start my own consulting business, which is called Polymer Technology Services. Again, this is the chapter on fatigue threshold that's in this very nice collection of crack growth in rubber materials book. So this review chapter came out in 2021. And before that, the last review really in this topic area was in 1988, a nice review done by Professor Anno Bomek. And so our review complemented that earlier work while presenting new experimental results, particularly on the cutting method, and also giving some new insights. So this is what I'll talk about today. I will give a brief introduction about testing for rubber durability, and then describe fatigue crack growth behavior of elastomers with a focus on showing where the fatigue threshold comes into that overall picture, and then how to measure the threshold. There's a variety of methods. Most recently, cutting method has been now commercialized. The Lake and Thomas insights from a molecular standpoint are pretty useful for us because they lead naturally into rubber formulation effects, elastomer type, cross-link density, and the like. And so I'll spend some time there talking about that interpretation, because when we start thinking about rational design of rubber compounds for durability, I think these insights are very useful and helpful to how do we make rubber better. I'm going to briefly, I believe there's probably a lot of folks here with an interest in tires. I'm going to propose a connection between fatigue threshold and tire wear just briefly. And so this gives you motivation to stay to the end of my presentation, and then I will summarize. So the most common way we use rubber is fatigue, cyclic fatigue at some lower strain than ultimate failure, many cycles until failure. However, the most common physical test you'll see in any rubber lab is the tensile test, where you just monotonically pull one cycle failure till the specimen breaks. Why is that? Why is there a mismatch between how we mostly test rubber and how rubber is used? Well, that's because testing time, fatigue testing takes a long time. So I think at the end of my presentation today, you'll see that within 1 or 2 hour testing methodology, we can get insights into a very long time fatigue performance of materials. So I'm mainly going to talk about crack growth today because the fatigue threshold is in fact related to this portion of the crack growth curve. However, if we're going to understand elastomer fatigue and fracture generally, I've kind of broken it down into these different areas: crack precursors in the material, which could be undispersed filler, contaminants, raw materials, and the like. What's driving the crack, the stress strain, strain energy density that's pushing on the cracks to grow, and then how fast the cracks grow are kind of dictated by this crack growth curve that I think you'll see a lot of discussion about today. So again, I'm going to focus on this one component, but keep in mind this bigger picture, and we need to understand all of these areas in order to understand rubber durability and predict product lifetime. So the talk today is about the fatigue threshold, which is this T0, T sub 0. And you can see that it's a lower limit of a fatigue crack growth. So if you plot log crack growth versus log tearing energy, there is some limit below which crack growth doesn't happen. And so this is a very important parameter because if you can operate somehow below this limit, then theoretically you could have an infinite fatigue lifetime, not including other things like aging or other changes to the material, of course. This has a lot of different names. So if you're hunting in the literature trying to get some information about this, you may see it called different things. Sometimes it's called the fatigue limit, intrinsic strength, threshold tear strength, and even endurance limit. And so just keep that in mind that these are talking about mainly the same thing. So it is a physical property of elastomers, and it is affected by rubber formulation, as you'll see later, especially the type of elastomer. And as I mentioned, if you can figure out a way to make a rubber part, operate below this limit, then it can have a very long fatigue lifetime. Again, not considering other life-limiting changes to the material. So you can see why this is a very important parameter, but it's also potentially difficult to measure because it's happening at very, very slow crack growth rates is where this shows up, meaning potentially long experimental time frames. So let me just briefly cover fatigue crack growth so you can understand the whole picture. Typically fatigue crack growth, we take some specimen. Oftentimes it's this so-called planar tension specimen with an edge crack, and then that crack is open and closed. I show here just a simple kind of sawtooth uh, strain function versus time, but it could be a sine wave or it could be a pulse. So I'm just showing this for as an example. And then you would watch the crack grow with a high resolution camera. And so you measure a crack growth rate, how fast that crack grows for a certain number of uh, fatigue cycles where the crack is open and closed, and then characterize that crack growth rate at different conditions. And actually, um, Dr. Stocek, who you'll hear from later, actually pioneered the use of two cracks on one specimen. So basically, it'll allow you to get twice as much information during a measurement. And this can even be fully automated, right? This is a Coesfeld tear and fatigue analyzer. And this particular version is testing 9 specimens simultaneously. There's 3 groups of 3, 3 here, 3, and there's 3 more behind the camera, which is moving. And then each specimen has 2 cracks in it. So you can see their potential exists for really collecting a lot of information about fatigue crack growth um, in an automated way. So you take that information and you would vary how much the crack is opened, small amount, larger amount, even larger amount, and that can be then converted to a tearing energy, and then allowing you to plot the crack growth rate versus tearing energy like I showed earlier. And it typically shows this power law response with an exponent F. And so this is the fatigue crack growth testing that's typically done. And here's some examples of natural rubber and butadiene rubber, basically formulated the same way in a carbon black filled formulation at pretty normal filler volume fraction that you would see in tire and automotive rubber parts. And what you'll see is, and keep in mind this is crack growth rate, so lower is better. It's not so clean to say that natural rubber is better than butadiene rubber. It really depends. At low severities, actually butadiene rubber has slower crack growth than natural rubber, and at the high severity end, there's a flip, and so there's a crossover. So, and we'll return to this later, and maybe this can help us understand why sometimes natural rubber is better than butadiene rubber for certain type of durability applications, and then sometimes butadiene rubber is better than natural rubber. In particular, butadiene rubber is better than natural rubber for small scale abrasion, wear resistance of tires. And natural rubber, on the other hand, is much better for very high severity cut and chip type damage of rubbers. But again, um, characterizing the crack growth curve allows us to do such a comparison of materials. So what I just talked about is this middle part of the crack growth curve here. Now, if you go even higher in tearing energy, eventually you're going to reach the tear strength of the material, and then you'll just have sort of catastrophic tearing uh, of of the rubber. I already mentioned the low end. We'll get to that later, but let's just talk about the tear strength because we can actually use the tear strength to get some information about T0, and we can use both of them together in some cases to learn about the slope of this curve. So let's start with the tear strength, TC. And there's a variety of ways to test it, but the key way to test this parameter is to put a predefined cut or a nick in the specimen. You have to have a macroscopic crack in order to measure the tear properties, um, which I always take this opportunity to remind people that the die-C tear, which is very popular in the tire and rubber industry, is not really a tear test. It does not have a nick or a cut. And so it's more like a crack nucleation test. Now, the geometry forces failure in this middle part of the sample, but it is not a true tear test. But a specimen like this planar tension one is very appropriate for making tear type test measurements, as well as the trouser is quite common. And if you use that geometry for the same 2 materials I showed you earlier for fatigue crack growth, what you can see is, and maybe this is not surprising, is that the tear strength of carbon black filled natural rubber is over 5 times the value for butadiene rubber. I think this is well understood. On the other end of the curve is this fatigue threshold that we're going to spend some time on. So we talked about the ultimate tear strength. That's kind of an upper limit. This now is the lower limit of the crack growth curve, below which fatigue cracking will not happen. So I'm going to give some examples of how to measure it. Before I do, though, the intrinsic strength that is underlying this threshold is the minimum energy to grow a crack in rubber is connected to the energy to break the polymer chains. So if these are two cross links, and this is the portion of polymer chain that's between those two cross links, as the crack grows through the rubber, it has to break all of these um, sections between cross links in the plane of the crack. So if you want to know how much energy it takes, then you can add up all those chains and find out the energy to break the bonds. And that's exactly what Lake and Thomas did to relate it back to some molecular things that we can use to compare different elastomers, for example. So, but we'll get to that in more detail later. Why is that so difficult to measure, the breaking of polymer chains? Well, when you load up the rubber from the far field, not all that energy actually makes it to the crack tip. A lot of that energy gets dissipated in front of the crack and never makes it to breaking the polymer chains. And so that's why the tear strength of rubber can be 10 to 10,000 times higher than this fatigue threshold for breaking all the polymer chains. The tear strength in magnitude is 10 to 10,000 times bigger than the amount of energy it takes to break the polymer chains. And that's because of dissipation. Hysteresis and energy dissipation, it kind of, some people view it as something negative in rubber compounds because of heat buildup and because of tire rolling resistance, for example. But if it wasn't for viscoelastic energy dissipation, rubber would be very weak material. So hysteresis is our friend when it comes to resisting damage development inside rubber. Now, the problem is if you want to measure T0, you somehow have to figure out how to minimize this dissipation in front of the crack tip so you get closer to only measuring the breaking of the polymer chains. So there are three different ways of doing that. One is to measure crack growth using fatigue crack growth like I showed you, but very slow, very low tearing energy near that threshold. The second way that I'll show is to use tear strength of swollen samples or at high temperatures. Why do we do that? Well, swelling and high temperature both are a way to reduce hysteresis, dissipation. So some way to take this big crack tip dissipation zone and shrink it down so that I'm mainly measuring the breaking of polymer chains. And then the cutting method, which does that minimization and focuses the strain energy density at the crack tip using a blade. So I'll go through all three of these. The first one is trying to get somewhere close to this downturn in the fatigue crack growth curve so that you can determine T0. Problem is when you do these crack growth measurements, where this turns down is somewhere around 10 to the minus eighth millimeters per cycle. And so what does that mean? Well, if you wanted to measure half a millimeter, even at 10 hertz, it would take 2 months. And so you can start to see the problem was trying to use this method to define where this curve starts to turn downward. And obviously 10 to the minus 10th is even higher. Um, One of the speakers today, Dr. Stocek, did a very nice job of doing this and really emphasized what we're talking about here. If you want to collect data in most of the crack growth curve, a few days is really all you need. And you can even have a really kind of targeted crack growth testing that might take 1 day. However, as you start to approach the really slow crack growth rate end of the curve, now it starts to take months. And so this is all the raw data that were collected, and then those were averaged to give this crack growth curve that I show over here. And what you see is the power law region, right, with slope F, upturn towards tearing, right? Eventually this is going to tear. And Radek actually saw the downturn and measured down to below 10 to the minus ninth to allow the determination of a T0. And he found a value of 47.7 for this carbon black filled EPDM. We'll compare this value to the cutting method later. But you can see, yeah, crack growth testing, you can get most of the information for the curve in a few days. But if you want to get anywhere close to the fatigue threshold in order to quantify it, then it starts taking really extremely high lab times. One method that folks have used to, again, try to minimize the dissipation at the crack tip is to either use swelling, so you can swell the sample, or you could heat up the sample. It's well known in filled rubber, in particular, that hysteresis goes down as you go up in temperature. Hot tear is lower strength than room temperature tear, right? That's what we're saying here. You do room temperature tear and you do hot tear at some increasing temperature. And if you plotted this versus some measure of dissipation, you could extrapolate to T0. So either through swelling or through increased temperature. So really what's going on here? Well, the fatigue threshold is not very temperature dependent, so it stays fixed. The tear strength, on the other hand, goes down as you increase temperature or you swell the elastomer. So what you're really doing is you're causing the crack growth curve to become compressed, and eventually, if you got rid of all of the dissipation, the tear strength of the material would equal the intrinsic strength or fatigue limit of the material if you could get rid of all the dissipation. So that's one way. So you could measure tear strength using trouser or planar tension, measure at room temperature, maybe 80 C, 120 C, for example, and you could then extrapolate to some T0. This has some problems that you might imagine. First, you can't completely get rid of all dissipation. If you go to high temperatures, when I mentioned 120 C in the last slide, if you're thinking about natural rubber, that makes people nervous. Natural rubber starts to degrade pretty readily above 100 C. If you're using solvents and doing swelling measurements, the solvent can evaporate during testing. And then if you do swelling, you have to correct the T0 because of the swelling. Because remember, the crack has to break all the polymer chains. So if you put solvent in the system, basically diluting the polymer chain. So you have to account for that. So the swollen ends up being a smaller value than the dry value. So you have to use the swelling ratio to relate between the two. And that just assumes that the only effect of solvent is just on pumping up the volume and diluting the system. Certainly could have other effects on the tearing of those polymer chains that really is not accounted for in this kind of analysis. And then finally, the method I'd like to focus on more today is this Lake and Yo cutting method, using now a commercial instrument, which is the intrinsic strength analyzer from Coesfeld. This is a commercial instrument, readily available. It was developed through a partnership between Coesfeld and Endurica, where I spent 4 years. And it uses a very well-founded cutting method of Lake and Yo that was out there in the literature for a long time. You know, I was a child when this paper came out, and certainly not thinking about reading rubber journals. But it took a long time, though, for it to be implemented commercially, just maybe about 5 years ago, 5 or 6 years ago. But now it's now on the market. Basically, if you look at this, this is a planar tension specimen, but it's turned sideways, right? So it's a planar tension specimen. It's turned vertical, and there's a cut in the specimen into which there's a blade that's pushed. So you can see it much better here. So here's a blade. So we still open the crack like you would normally for a tear strength measurement or a fatigue crack growth measurement. Open the crack, right, at some given tearing energy. And then while the crack's open, push a very sharp blade. You can see this is 2-micron bar here, a very sharp blade, push it into the crack while it's open. And it's not a single measurement. You have to make measurements at several different points. And the whole goal of the blade is to localize the strain energy density. If you just open the crack from the far field, as I mentioned earlier, a lot of that strain energy density doesn't make it to the crack tip because of dissipation. But when you push a blade into the tip, it localizes the strain energy density to minimize dissipation. And that was shown with a very basic finite element simulation. If you take this is just a 2D simulation. If you do a hyperelastic simulation in Abacus and you put a crack, if you open up that crack, you can see this these colored regions here showing that what you're doing is out in front of the crack as well as at the crack tip. And when you push a point load into that open crack, now everything shrinks down. It's a very localized strain energy density region. So that was a nice simulation that Dr. Will Mars did to show how the cutting method can minimize dissipation. So as I mentioned, it's a series of measurements. So you open up the crack at different levels, and then you very slowly push the blade in. We also make measurements at other faster rates first, and then slow down to this final very slow cutting rate, and for which the data is shown here. So you can see these data points here are collected at very low crack openings. You get some frictional contributions from the blade. If the crack's just barely open, you're pushing the blade in, there can be some friction. And then you do start to see some hysteresis contributions that can show up at high tearing energies. But you can see that there's a place where this behavior is minimized. And that's what basically was proposed by Lake and Yo, is that you have your normal tearing energy, that's the blue, and you have the cutting force, which is coming from the blade, and there's this intrinsic cutting energy, S, that comes out of the measurement. And I've taught classes where I go over this method, and it involves plotting F versus T, and then you have to use a line with slope of -1, right? Basically just rearrange this equation. And that allows you to find out when you fit through these lowest data points, get this SC, which is 482. But I saw a lot of puzzled looks every time I taught this, every time I mentioned this. And then one day I suddenly realized there's a lot easier way to understand this. If you add the F and the T together, you can plot that versus crack opening strain. So here's F plus T. We're going to plot it as a function of crack opening strain. And what you see is it's minimized. And where it's minimized is that same value, S0C here. And so here's carbon black filled natural rubber. Here's carbon black filled butadiene rubber. And without doing anything to the data yet, to actually pull out a T0, you can already see that pushing a blade into carbon black filled butadiene rubber is almost requires double the force compared to natural rubber. Say, wow, I thought you just told me earlier that the tear strength of natural rubber is 6 times higher, nearly 6 times higher than butadiene rubber. Remember, this is at the other end of the crack growth curve. And you can now already see that there's going to be a flip of behavior. Now, butadiene rubber is showing much better crack growth resistance. So you can see that we don't have T0 yet. We have this so-called S0. So what Lake and Yo did, they said they plotted the quick cutting method value that I just showed you, and they compared it to T0 that was measured from that near threshold, very long fatigue testing that I showed you an example from Dr. Stocek earlier. And what they saw was that these were related to each other. And the difference was this constant, which was related to the blade, right? How sharp the blade is, etc. So one of the key things that's needed in this method is a control material for which you know T0, and then you can measure S0 using the same conditions in your other experiments. So that was done here. So I showed you the data for carbon black filled natural rubber and butadiene rubber, 482 and 949. Our control material was an unfilled SBR it had a value of 572 and had a known T0 of 60. So based on that known value of 60, we can determine B. That can then be applied to the other two materials. And what you see is that the fatigue threshold for butadiene rubber is about double the fatigue threshold for natural rubber. But both of them are much smaller than the tear strengths for those materials. So you can see that here. Here are the tear strengths, 50 and 99.6. And sorry, the intrinsic strengths, the fatigue thresholds, 50.6 and 99.6. And then the tear strengths I showed you earlier are much higher, 18,500, 3,000. And what we learned was, if you assume some very fast crack growth rate for TC and some very slow crack growth rate for T0, 10 to the minus 2 for TC and 10 to the minus 8 for T0, you could actually plot those data points. So here's natural rubber, 18,000. Here's butadiene rubber, 3,000. You can plot those two data points on here. And then you could do the same at the low end. And what you see is butadiene rubber is here and natural rubber is here. And if you just draw a straight line between them, it almost captures the actual fatigue crack growth data that were acquired from testing. So this was a sign that if you know the two ends, you know the tear strength at the upper limit, and you know the fatigue threshold at the lower limit, that knowledge can give you an approximation for what's happening in between, and you can even reproduce the crossover simply by drawing a line between those 2 points. So we showed that this actually works pretty well for a large variety of rubber compounds. If you get a crack growth slope F from fatigue crack growth testing, and then you get a value of F estimated from T0 and TC. Remember, I told you we can assume 6 decades, right? So here's 10 to the minus 2, here's 10 to the minus 8. That is 6 decades. So that's where that 6 comes from. It comes from RC over R0. And then if you take log of TC over T0 on the bottom, you can get a measure of F, right? It's just this over this. And when you fix the RC and R0, then all you need to know is TC and T0. And so, yeah, it works quite well. Now, I would never want to replace fatigue crack growth testing with this 2-point method, right? Because you could be off by quite a bit. So if you're doing some very detailed predictions of fatigue, that's not necessarily the best thing. But for a first approximation to compare materials, then I think this is a possibility. Dr. Will Mars was very kind to me, and he started calling this the something like the Robertson rule or the Robertson ratio. Anyway, I don't call it that, but Will has been nice and called it that on occasion. So now we can compare this cutting method to the near threshold fatigue crack growth. Again, that very long experiment of 7.5 months that got a value of 47.7. And what you see is, using this ISA cutting method, you get pretty close, nearly identical in only 2 hours. And so you can see the value of this technique and why it's really going to change the way people are able to quantify this fatigue threshold. So that brings us into this Lake Thomas molecular theory and some rubber formulation effects. They kind of dovetail nicely together. So Lake and Thomas, again, taking this picture that in order for a crack to move through rubber, the minimum energy required is energy required to break all the polymer chains. So this chain is already broken, and the first thing that happens is the crack stretches the chain between the crosslinks. One of the assumptions in their approach is that these crosslink points don't move. Maybe that's not realistic, but again, that's one of their assumptions. So first thing is the crack has to become stretched. That's where this molecular weight between crosslinks comes into play. You have to energize all the bonds in the polymer chain, stretch them till one can break, and then the polymer chain breaks. And what you see is there's some really nice things in here that a polymer chemist and a rubber scientist can use to figure out what's happening in a rubber compound. The first one is crosslink density, right? That's explicitly in the model. The other one is molecular weight per backbone atom. That has to do with the repeat unit of your polymer, chain stiffness, also a backbone polymer chemistry, bond length, bond association energy. All of these relate to the building blocks for the backbone of the polymer. And so, and what you can see is that if you hold everything constant and you change only the elastomer type, the main area where things are going to change are this M0, molecular weight per backbone atom. Smaller is better. Notice the minus sign here. And chain stiffness has a positive impact on fatigue threshold. And so we made some measurements on carbon black filled elastomers, different elastomer type, natural rubber, isoprene rubber. Obviously, chemically, these first two are very similar to each other, butadiene rubber and an emulsion type SBR. And the M sub 0 is the molecular weight per backbone atom. It turns out to be 17 for polyisoprene, whether natural or synthetic. Butadiene rubber is much smaller at 13.5, and then SBR is 19.6 because of that heavy styrene group. And what you see is if you compare natural rubber and butadiene rubber, the M sub 0 exactly explains what's going on. You get a much smaller M sub 0 for butadiene rubber, and you get a much higher fatigue threshold, 80 instead of 20. SBR is not just an M sub 0 effect because SBR is also has higher chain stiffness. So that one it needs chain stiffness to come into the discussion to understand where it fits. But the relative ranking is lowest is natural rubber, highest is butadiene rubber, and in between is SBR. And that's exactly what the classic work of Lake and Yo showed on unfilled elastomers. So our work was on carbon black filled elastomers, and their work was using unfilled elastomers. But again, butadiene rubber is the highest, natural rubber is the lowest, and then SBR is in between. And you can always blend elastomers too, right, and get something, in the middle. So other elastomer types were shown by Gent and Tobias. So they also brought in polydimethylsiloxane, which is the main building block of silicone rubber, and a fluoroelastomer. And they plotted things as a function of crosslink density or molecular weight between crosslinks. So as you go this direction, you're getting more crosslinks, higher crosslink density. And what they showed was, compared to the crosslink density prediction of Lake and Thomas, about a factor of a half, they fitted these and they varied, but they were in the right direction. They were positive slopes, and some of them were quite near to a half. And so that was generally shown to be in agreement. And then the elastomer type effect, it's a lot easier when you normalize the M sub C by the M sub 0 for the polymer, and that's what's done over here. So this is converted to here simply by dividing by M sub 0, and I'm going to show that on the next slide, so we can look at elastomer type effects. And what you see is, out of all of these elastomers, the best is butadiene rubber, cis butadiene rubber. Below that is natural rubber, and really at the very bottom are things like silicone materials and fluoroelastomers. These materials are intrinsically weak because they have fat polymer chains, right? This dependence on M0 that's in is smaller is better. So that means a lighter backbone means a skinnier polymer chain. And so it basically means more polymer chains have to be broken per area And so therefore that leads to a higher fatigue threshold. And so you see something like polydimethylsiloxane and fluoroelastomers have really high M0s, and they have very low fatigue thresholds. So the elastomer type effect can be very nicely rationalized based on this molecular theory. When we dug ourselves into cross-link density effects to try to see if this, this prediction held, what we generally found is we did not agree with that prediction. But we didn't do a lot of testing. This was just a couple of systems that were looked at: carbon black filled SBR, and then something that looks like a passenger tire tread, a blend of SBR and BR rubber with silica and silane. And when we plotted fatigue threshold from the cutting method versus the loading of sulfur in the formulation, and we adjusted accelerator to keep the typo crosslinks similar, we didn't see the expected trend, which would have been a downward sloping relationship. So there's still some work to be done in this particular area. Oil is a relatively simple thing to rationalize because, again, it's related to that swelling effect, right? If you add oil to the rubber formulation, it pumps up the volume and dilutes the polymer chain. So based on the swelling discussion I had earlier, you can actually determine a swelling ratio based on the amount of oil you're adding and the density of the oil relative to the polymer density. So it's pretty typical to buy oil extended elastomers like SBR, and oftentimes they have 37.5 parts of oil. And I was curious, if you did this kind of analysis, what would happen? And what you find is that oil extension reduces the fatigue threshold by about 20%, almost 20%. So if you want to have a rubber compound that has high durability, long lifetime, taking out oils, low molecular weight things is generally a good strategy. Filler effects. Um, Before we had access to the cutting method, the only literature that was out there was really from swollen tear strength. Again, using that approximation method, where if you swell the sample and measure tear strength, you're getting some of that hysteresis hopefully removed and getting closer to measuring the actual fatigue threshold. So this previous work published by Bomick and co-authors showed very striking effect of filler volume fraction, carbon black, and even some clay on the fatigue threshold, both in natural rubber compounds and in SBR. But again, this was approximation method using swollen tear strength testing with the limitations I mentioned. We did this ourselves, again with EPDM at 3 different carbon black loadings of N550, SBR 3 loadings of N339, and this tread silica formulation that I just discussed. And if anything, we saw the opposite effect, or at best, basically flat. So we did not find a significant effect of filler volume fraction on the fatigue threshold, at least in our rather limited measurements so far. And if you go back and I always like to really kind of drop these schematics so I can see the relative sizes of things. So if you take something like N110, which is one of the smallest particles of carbon black we use in tire and rubber, and you compare it to the average distance between crosslinks at a normal crosslink density in rubber compounds, what you see is this Lake and Thomas picture completely changes, right? Remember, we had to grow the crack and break all the polymer chains, but look how huge even the primary particle of carbon black is relative to that. So I think there's a lot of fundamental work to do on understanding filler effects on fatigue threshold, and certainly we showed more experimental measurements are needed to really clear this up. So what happens? Does the crack have to go around the filler particle, or does the filler particle itself have to fracture? It's not known, but you can see from the relative time scale, size scales, that simple picture that Lake and Thomas put out does not help us understand what's going to happen with filled elastomers. So the last thing I promised to get to, and I think I have just a couple minutes, is this proposed connection between fatigue threshold and tire wear. Um, and I'm not talking about cut and chip wear resistance. I'm talking about small scale, low severity abrasion. And obviously there are micro asperities on the road, and they give a range of tearing energies to the tire tread, which depend on how big the asperities are and also the normal load and slip conditions on each asperity. So what you see is it's a heterogeneous situation with respect to spatial considerations and also load intensity considerations. And so fatigue in rubber starts with crack precursors, and then those cracks grow and eventually intersect, leading to tire wear. So this is just the mechanics piece of tire wear, obviously. So, it doesn't include other pieces of the wear understanding, like thermal oxidative breakdown of the material and other contributions. But at least some of wear we can understand from this sort of micromechanics. And you remember that the fatigue threshold for butadiene rubber is about double the fatigue threshold for natural rubber. And one of the mysteries I've always scratched my head at is, why should natural rubber have worse wear resistance than butadiene rubber? And I think this picture can help understand that. If you have a distribution of tearing energies that are happening, again, from that very heterogeneous situation at the surface where road asperities are sliding past the surface of the road, and there's some distribution of these, anything below the fatigue threshold, which is here for natural rubber and which is here for butadiene rubber, will not contribute to damage. So if you have a higher fatigue threshold, then some of those events that are happening at the surface won't cause crack growth. And so based on this, we can understand that the higher fatigue threshold for butadiene rubber may be one of the reasons why it has better wear resistance than the fatigue threshold than natural rubber. But what about the TG effect? There is this tire industry heuristic. Lower TG is better for wear resistance. Based on dissipation in front of the crack tip, this never made sense to me from a crack growth perspective. If anything, higher TG should be better. But we have to remember that there's very few polymers that are actually used in tire treads. It's essentially only BR, SBR, and natural rubber. And so my perspective is, it's not lower TG that's better for wear resistance, but rather more BR in the formulation because of this ranking of fatigue threshold. BR is higher than SBR, is higher than natural rubber. And it's about twice, BR is about twice the fatigue threshold of natural rubber. I showed you the Lake Yo cutting method that's now commercially implemented on the intrinsic strength analyzer. It can characterize a fatigue threshold in about 1 to 2 hours. And if you compare that to near threshold fatigue crack growth, which takes months, now we have a really quick method to assess this key parameter of rubber. If you take that parameter and you combine it with a tear strength, you can get kind of a first pass approximation of the power loss slope for fatigue cracking. Lake Thomas gave us a nice molecular view of fatigue crack growth at the fatigue threshold limit, and it generally predicts elastomer type effects. However, cross-linking effects and filler effects need to be studied further, and with no real consensus yet. And all of the literature prior to the intrinsic strength analyzer was mainly estimated from tear strength of swollen samples. And that may be one of the reasons why we have some disagreement among the data results. And I'm very happy that you joined my webinar today.
From my side, thank you, Chris. It was very good presentation, a lot of informations, and you have presented that in a very nice manner. We can continue with the next presentation if there are not.
I
now.
see some questions, but I can address those in the chat, Professor Heinrich.
You can do that maybe during the next presentation in the chat, and we would
Yes.
like to stay in the time frame that we have given. And I would propose that Dr. Ghosh will continue with his presentation now. Is this okay?
Yeah, excellent.
Yeah, is my slide visible? Can anyone confirm?
Yes.
Okay. So, good morning, good afternoon, and good evening at respective places across the globe. So, before I begin, I would like to thank the organizer for organizing this webinar on influencing lifetime of rubber. And it's a great privilege for me to present our chapter published in this book that is titled Fatigue Crack Growth versus Chip and Cartware of NR and NR blend-based rubber compounds. So this is a joint work done with Dr. Radek's group along with our other colleagues. So basically this presentation will be focused on two different compounds based on trade rubber, and specifically this application part, as my previous speaker has explained about the fatigue threshold. Those concepts will be used in our work very much for characterizing the different properties. And I will like to start with some of the basic concepts or basic information about the tyre. Maybe the audience, maybe some of the people may not be related to tyre. So just to make a connection with the audience, I will begin with some of the basic performance requirement of a tyre, and then I will take it forward with respect to our particular work. So the presentation.
Can you switch? Sorry, can you switch to the presentation mode?
Yeah, is it? Can you see the next slide now? Is it visible? The content slide?
Yes, we see that. But I suggest to switch into the presentation mode so that we have then the slides larger on the screen.
Okay, it's showing here. I'm not sure.
If it does not work, it's okay. Okay.
Yeah, we see now the actual slide as well as this next one.
Okay, okay. I'll just do one thing.
Maybe share it as a desktop. If you will share as a desktop only, then we will see only the actual slide.
Yeah, now we have seen the overview about the slides. Yes, yeah. yes. Perfect.
Okay. Okay.
Perfect. Yeah.
Sorry for the short interruption. Okay. So the presentation flows will be like this. I will start with introduction about the tyre and its performance requirement, and then we'll talk about the background and motivation. Then we'll discuss about the objective, followed by material and experimental methodologies used, and we'll discuss about the results. And finally, we'll summarize. So if you see a tyre as a vehicle component, it could be anything. It could be a two-wheeler, it could be a four-wheeler, or it could be a commercial vehicle. So there are 4 or 5 different functionalities which it has to perform. So first of all, it should carry the load. Then it should assist you in handling, like acceleration or braking. It should provide you the ride comfort, specifically with respect to the noise, vibration, and harshness. And it has a good contribution with respect to the fuel efficiency or fuel economy because of the rolling resistance. And the last two parts are related to the safety and durability, which are interrelated. So safety with respect to the braking distance on the wet roads, or durability, like if it tire hits on the pothole or some nail, so tire should not fail, or it should show some resistance so that the passenger will not be in trouble. And today's presentations are also, the topics are also related to the safety or durability with respect to the fatigue crack growth or cut and chip. So if you see, there are the classification as per the tire wise, you can say the two-wheeler tires, so there are major performance requirement like handling. It should be stable, it should provide the grip and ride comfort, and safety is definitely one component which is performance requirement for all kinds of tires. Then if you go for passenger vehicle, the matrix is slightly bigger. It starts with handling, ride comfort, noise, vibration, fuel efficiency, traction, and safety. Moving to the commercial vehicle, then your load carrying is the biggest requirement, and where resistance also comes into play. Then fuel efficiency is also another major important criteria, and cart resistance, because the specifically for the trucks and all, because of the heavy loads, as well as the roads are not paved completely, so cart resistance is important. Then another criteria called retreadability, the putting the rubber when the tread gets torn off, wear out. And safety is another important parameter. If you go for the off-highway tires, the vehicles, load carrying, then tire temperature is another criteria, and cut and chip resistance is the most important criteria to be fulfilled. Traction, specifically when the soil is loose, and the safety component as well. So in all the cases, you can see the safety is important parameter for a tire, because it is the only contact between a vehicle and the road. And with a specific reference to the cut and chip resistance or fatigue crack growth, our presentation will be focused on that area, how to measure for a specific few compounds. So before I go to that, uh, I would like to give some historical perspective of tire failure, and I will not take much of your time just to explain the history. However, all of you, maybe those who are in this generation tire technologists or the previous generation tire technologists, they know the Ford Firestone fiasco, and it has a relation with the fatigue crack growth. So just to link with that, I'm trying to give a few facts. So two personal friends like Harvey Firestone and Henry Ford started their corporate relationship in 1906. So Henry Ford, who chose to outfit Firestone tires to his new Model T, which was one of the what to say most famous car in those days. In 1990, the Ford Explorer began to lead one of the greatest automotive revolutions in history. Globally, it remains a popular Model T today. However, journey of Explorer epic popularity was not so smooth. It has a troubled history. What was that? I will try to explain in a very brief manner. And and another important fact, that between 1990 and 2000, the NHTSA received a large number of complaints regarding tire failures on Ford Explorers equipped with Firestone ATX, ATX2, and Wilderness 80 model tires. And it actually ended up with so many road accidents, and some of the people also died on the road accidents. And in results, Firestone and Ford Motor Company had to recall and replace about 23 million tires. It cut the market value of Bridgestone and Firestone in half. So this is the fact about the Ford Firestone issues, which was reported in early 2000. And why it happened, actually, if you go to the basic fundamentals, those days, in the Ford Explorer, they introduced the front suspension, independent front suspension. So it gave a smoother ride to the passengers, but it came with some cost. What it is that? So when there is a vertical movement, specifically when it was moving over a bump, that actually offsetting the camber angle of the front tires, and which was very much affecting the high speed stability, and there was a chance for rollover as well. So how to fix that? So Ford decided that let us reduce the front tires inflation pressure a bit, and that gave some relief, but it came with a cost like the tire failure. And this failure was analyzed by Dr. Sanjay Govinci, and there is a Firestone tire failure analysis report also publicly available, and which actually given the what to say that analysis that the belt separation has happened in this area. You can see that is actually created because of the fatigue crack propagation between the rubber layers between the two belts, not at the interface level. So that's the reason actually I wanted to bring to the notice of the audience that fatigue crack growth is so important, and which has a relation with the tire failure as well. And it can be related with the many other things which is not catastrophic in nature, like the tire wear, as Dr. Robertson also uh, mentioned in his presentation. Okay, so these are the typical tire failures, and you can see there is a cut on the tire sidewall. It could be due to the impact to the potholes or road curves, and the belt edge failure, which we just explained. Then there could be failure in the bead area as well because of the improper treatment with the vehicle on the vehicle rim. Then the inner line is split, and the right corner is the tread cotton chip, which is very predominant in basically the commercial vehicle tires as well as in the off-road tires because of the road asperities, because the road asperities are not so smooth, and sometimes those vehicles are operated in the mines, specifically on the iron road mines, and all the ores are very sharp in nature, and those things actually create the cotton chip. And this cotton chip actually in general, it appeared in the later stage, later part of the tire or per tire life. Let us say if the one tire is running about 1 lakh kilometers, so maybe it may be happening at the end of its life, maybe more than 70,000 or 60% of its life or 70% of its life. And these are the few of the pictures. You can see that actually a real picture of a tire which has got a lot of cuts and chips on the tread surfaces, and it has got many implications because these cuts and chips or the cuts can propagate inside, which can degrade the rubber inside rubber, and more importantly the moisture or water can enter through these cuts, and that can corrode the steel belts underlying the steel belts, and that may cause a catastrophic failure. And why it is happening, as I explained, that the tires are not running on a actual very smooth surfaces. Many of the times it is encountering very rough surfaces as well. And as the tire uh, in the market for a long time, because of the exposure to the different weather conditions, rubber also gets degraded, and combinedly the tire the cuts and chips are getting generated. So that is one of the major problems can be seen in the practical life, specifically for the truck bus tires or the commercial vehicle tires and the off-road tires. Now, if you see microscopically that this asperities creates different kinds of stress histories or the dissipation characteristics. So if you can see in the green portion is actually having higher, what do you say, higher dissipation compared to the blue portion. And when the tire rotates, its contact patch, maybe 20 degree of the segment, total segment, or 25 degree of the segment, depending on the load, actually comes in contact with the road and loaded. And if you see in the time scale that 10% of the total rotation time is in the loaded condition, and 90 rest of the time it is in the relapse condition. So if you see the graph, it is the more of a pulse type of loading, and initially it is getting the amplitude is what to say for a very short period of time it is loaded, and rest of the time it remain unloaded condition. And taking the clue from this particular slides, we will also be using this information for doing our fatigue crack growth testing, and using this what to say um, methodology. So what is the objective of this particular work? So develop laboratory test method that can simulate the realistic live operating condition that can predict our performance with respect to carton chip behavior, which is very important. At the same time, also the quantitative determination of the complete Parrish-Aragon curve characterizing the FCG behavior from endurance limit up to ultimate strength. So already Dr. Robertson had given a complete detailed account of the threshold, what is the threshold or endurance limit or intrinsic strength. He made my task much easier, which already you people have, the audience has already got the detailed information about it. But for the sake of keeping the connectivity with my work, I will try to explain things in a much simpler way, or what to say, very quick introduction. I'll give it to this particular part so that it will not be a repetition of what Dr. Robertson has just spoken a few minutes before. So that starts with the endurance limit T0, which is also called the intrinsic strength, then stable crack growth zone, that the steady state zone, and ultimate strength or critical TN energy. So one important point which I must mention here, and also Dr. Robertson has mentioned, that about the endurance limit, intrinsic strength was not talked much in the literature. If you see that maybe the 1978 by Lake and Yo, and later the Professor Bomick gave some of the things, but due to the unavailability of the proper instrumentation, it was not explored so far. However, the work by Dr. Robertson, Dr. Heinrich, and all actually enriched this particular aspect in a great detail in last 10 years, or maybe last 6 years, 5-6 years. There are a lot of publications have done, and it is really nice to note, and it is really contributing to the understanding of the rubber fracture mechanics very much. So it will be unfair if we do not talk much on talk at least some of the basic points about this, which I'll be using it for, which we'll be using it for our work as well to explain the things. So I'll just quickly go through the next few slides. So don't get upset about the long, what to say, the busy slides. So basically, as this strength of rubber depends on its chemical structure as well as on the viscoelastic behavior occurring in the crack tip near tip fields. Basically, the strength is derived from the viscoelasticity. So far, the classical rubber technologies or the rubber technology education says that the natural rubber has a crack initiation is early, but the crack propagation is delayed, and vice versa for the synthetic rubber. So that was a statement. Altogether, it was a statement. But after measuring the T0 values, and a lot of work has been done, as I mentioned, this can be quantitatively explained for different types of rubbers, why this is so. And if you see the complete crack growth curve starting from the threshold level to till the ultimate strength or critical tearing energy, this is very clear. So that's the reason the synthetic rubbers actually derives its strength from this viscoelastic energy dissipation. And therefore, total energy required to propagate a crack in rubber is usually significantly greater than the energy associated with the intrinsic strength of the molecular structure. And there is a minimum energy requirement for propagating this crack or cutting this polymer chains. And this minimum energy depends primarily on the details of the polymer network, such as average molecular weight between crosslinks and on the weakest bond in the main polymer chain. This is also explained in detail in the previous presentation, and it is therefore often called the intrinsic strength since it reflects the polymer chemistry and the network. So this is just an overview between the fatty crack growth and cutting, as taken from the Robertson's previous paper, which was published in Tyre Science and Technology. And you can see that there is a lot of energy dissipation in front of the crack tip when we do the fatty crack growth. However, it is if you hence, however, in the case of the cutting, if the crack in the front of the crack, if the dissipation is higher, then it will be difficult to measure the threshold strength. So therefore, one need to be very causes about the testing procedure, which was also explained in their paper very nicely, which was also and is being used in present work as well. So intrinsic strength marks the lower limit of the fatigue crack growth rate curve, and below this, the crack will take infinite time to propagate further. So that can be as the endurance limit, and this is very important while you design a product like a tire or any rubber product. So if you know that this is the threshold limit and your operating condition is below this, then you will be very safe. The next part is the critical tearing energy, which is actually the another extreme of the fatigue crack growth curve, where it fails completely, the catastrophic tearing occurs. And in between, you have a stable crack growth zone, which is now also very recently, there are a lot of publications on the stable crack growth zone. Therefore, T0 and TC defines the window within which crack grows due to the application of cyclic deformation. So coming to the material, the rubber compounds, there are two different rubber compounds were used. One is 100 parts of natural rubber compound. Another is the 40 parts of natural rubber and 60 parts of styrene butadiene rubber. So see how that is the difference, and the fillers are all different. And it was also shown by Dr. Robertson that filler has not a very significant role with respect to the T0 or threshold limit. So we'll coming to so there are different experimentation was carried out, all made by Coastville. The first with the intrinsic strength analyzer. So there we have used the pure shear specimen of 10 millimeter into 100 millimeter into 1.5 millimeter thickness and pre-cracked at one edge, and strain percentage was 0 to 50%, so that we have a different tearing energy level, and cutting speed was kept at different speed like 10, 0.1 and 0.01 millimeter per minute. So in concern to the tear fatigue analyzer, the stable crack growth zone, mini pure shear or mini plain strength sample specimen was used with the following dimensions, and temperature was kept about 70 degrees centigrade. And the frequency as the Gaussian pulse waveform with pulse width of 100 millisecond and loading frequency of 5 hertz, or repetitive frequency of 5 hertz, which was again taken from the previous slide. If you recall that the loading pattern is of more of a pulse in nature compared to the sinusoidal in nature, and RRC was kept 0. And the next experiment was done for the chip and card tester from the ICCA instrument. This is again made from the Coastville, and this is the instrument, and this is the type of rubber specimen used, which is having an outer diameter of 55 millimeter and 26 millimeter of inner diameter, and rotation speed kept about 200 RPM. And there are different normal forces we have measured, starting from 70 to 170. And the impacting frequency was 5 hertz and impact time was 200 milliseconds. So output will be, so under that impact nominal forces, what are the shear forces which is responsible for creating the cuts or chips. So those will be measured. So coming to the results for the intrinsic strength, so these are A and B. A is for natural rubber compound and B is for the natural rubber SBR blend compound. And these are the plots are the cutting force versus time. And you can see at the low tearing energy level, in the case of NR-SBR, there is a sharp peak initially, and then it is a smooth in nature. Another observation could be made from this thing that there is a lot of fluctuation in the case of the natural rubber based, or we can call it the stick slip mechanism or stick slip effect. That is due to the strain induced crystallization effect in the natural rubber, which is not that much prominent in the case of NR-SBR blend. So after that, after this cutting force versus the cutting energy versus tearing energy is plot, and the detailed explanation has already been given in the previous work, and this can also be found in the literature. I'm not going to discuss about how these things are measured. However, this is the curve for our compound, the natural rubber and the natural rubber SBR compound. And intrinsic strength for natural rubber based compound was 49 joule per meter square, whereas for the NR-SBR about 61. So 60 parts of SBR addition has helped in achieving higher intrinsic strength. So the threshold limit has increased, and it was also shown in the previous work that natural rubber is about 40, and if you go for BR, it will be much higher, almost double. and SBR is in between. And these results are also in line with that observation as well. So this is the stable crack growth zone, crack growth graph for these two compounds, NR and SBR compounds. And throughout the tearing energy zone, the NR has a lower crack growth rate compared to the NR SBR plane, which is also explainable from the previous work, as well as from the theoretical point of view, that after a certain tearing energy level, NR is having a better crack growth resistance due to the strain-induced crystallization effect. And this table also gives the material parameter from the power law model as well. So coming to the critical tearing energy, so this is also measured in the ISA measurement, and you can see that although inner compound was having a lower threshold limit, however, when we talk about the critical tearing energy, which is quite high compared to the inner SBR compound, so 16,688 versus 14,095. So critical tearing ultimate strength is of NR is higher compared to the NR SBR. So based on all these informations, the complete graph was constructed, and you can see the red dots that threshold limit for NR compound is lower compared to the SBR, NR SBR compound. However, at the higher tearing energy zone, it is again doing showing the higher critical tearing energy. And of course, the stable crack growth zone or steady state crack growth zone, NR compound is showing the higher value. So one should be very careful while interpreting this data and relating with the practical application. So we must understand where the practical application lies actually, the tearing energy level. So that is very important. And we'll also explain these things when we're discussing about the cotton chip behavior. So the ICCA results or cotton chip results, this is also done by the previous work. The majority of the methodologies were explained there, and the CC damage parameter introduced by Dr. Heinrich. And what is this? This is the parameter called P. So the lower the P value, better it is. And it is an integration of the force at the maximum force to the minimum force divided by the number of cycles. And you can calculate these values at different cycles level, and which is plotted for these two compounds in the next slides. And you can see the damage parameter. And one interesting observation is that for the natural rubber based compound, the left side curve, till maybe the initial energy level, initial force level, natural rubber was showing higher damage parameter, damage values compared to the inner SBR compound. However, it got reverse gets strain. Strain gets reversed at higher force level, which is explained in the next slides as well. So you can see very clearly that the inner curve is smoothly linear increase. However, inner SBR is passing through a small minima, and then it is again crossing the inner curve. So you can see that for inner SBR compound, the damage is low, maybe up to 130 Newton, the normal force. And after that, it is showing a higher values, specifically at 150 Newton. So therefore, one should be very careful while selecting the compounds with respect to the application part. And this is also another challenge, how to quantify the tearing energy level or the severity level from a very smooth road to a very high very rough road. So which is practically impossible to do that. Therefore, we need to see the things at a wide energy level. The properties needs to be measured at a quite a high wide band, so that you will not be in trouble when it goes to a practical application. So this is very important graph, and we can see that that fatigue crack growth also, that inner curve was showing a slight lower crack growth rate compared to the inner SBR compound, and which is also coming through your cotton chip behavior at particular energy level or force level. So in summary, the complete fatigue crack growth characteristics of rubber from endurance limit up to the ultimate strength is determined for these two compounds. Non-crystallizing SBR exhibited higher threshold of intrinsic strength compared to the strength crystallizing inner, and FCG rate in the stable crack growth zone is lower in inner compound compared to the inner SBR compound. Ultimate strength of inner compound is higher than that of inner SBR compound. Chip and card behavior of inner SBR compound is lower at low force level compared to inner compound, but the trend gets reversed at higher force level. So that is the key while you use it for a practical application. So at the end, I would like to acknowledge my co-authors and with a special mention to Dr. Stocek for extending his kind support in all respects. So thank you all for your for patiently listening the talk, and thank you.
Thank you, Dr. Ghosh, for your presentation. I think this is especially very interesting for people that are working in tire industry, where these blends NR, SBR, and L are used under these specific conditions of loading. The same like the same thing is valid like in the last presentation. If someone has some questions, please write these questions in the chat. And if there is sufficient time for you, Dr. Ghosh, you can answer to that or write an email later back. We are a little bit in delay. That's why I would like to ask Radek Stocek whether he is ready for his presentation. I think it is so. And
yes, I'm ready, and I will start immediately. Thank you very much, Professor Heinrich. I will share my screen now with the presentation. So it's here. Okay, so do you see my screen, please?
Yes.
Okay, great.
Yes.
Thank you very much.
Perfect.
So, okay, so thank you very much for introducing me. Thank you very much for all you are coming and hearing our presentation and our webinar. I am really very happy to be here and to could share with you results we presented or published within our book. So the title of my presentation today is Advances in Experimental Characterization of Complex Fracture Behavior of Rubber. And in general, what about I will speak is the Paris-Erdogan plot, or respectively, let's say, fatigue crack growth characteristic. So I will focus now on two papers we presented within our book with my colleagues. The one is some revisions of fatigue crack growth characteristic of rubber, and the second one is determining parametrical functions defining the deformations of a plane strain tensile rubber sample. So let's go. Yeah, if we see now such a, let's say, the real cases of a damage on a tire as an example, let's say the industrial request would be to optimize the rubber resistance against real damage still within the phase of compound development. This we need to solve such a question. So how we will describe and determine the fracture behavior for a product which is loaded cyclically, that's that fatigue crack growth characteristic, which is, let's say, from 60s last century, presented from a Lake and Lindley here with this diagram for two materials as an example. This is an NR material and SBR. Both gentlemen, Chris and Dr. Ghosh, spoke about these two materials as well and presented this characteristic. So you know this very well. And I will go more in detail regarding this characteristic. So this we can divide in 4 different phases. So firstly, we have a region at the first phase is there is a region where no crack initiation and crack growth occur. Mainly there is some issue in ozone and so on, and the chemical problems and so on. However, no crack initiation. Then firstly at the T0, which is the intrinsic strength, endurance limit, the crack is initiated and then starts. Let's say we need even to understand crack initiation means even that there is a crack. in the rubber material. However, this crack doesn't propagate. And firstly, when we will be over this energy, which is associated with T0, then even in a crack, the crack is initiated and propagate. This we need fully to understand. Then we have a phase 2. Let's say the phase 2 is defined with this equation, and let's say this is a nonlinear characteristic here within this diagram, and coming in an interface between between the next phase 3, which is well known as a stable crack growth propagation, or Paris law, which is here as well written. So we see that there is an exactly the power law for both materials. However, there is even as a one transient point here labeled. And then we have a phase 4, which is let's say non-stable, unstable crack propagation, very close to T0, TC, critical tearing energy, and over or close to critical tearing energy. That's an energy where the crack is not possible to stop anymore. So like that. So let's go more in detail in this characteristic. And we have a T0, which is an intrinsic strength, as Chris introduced, which is the minimum energy primarily depends on the details of the polymer network, such as the average molecular weight between the cross links and on the weakest bond in the main polymer chain. This table was shown as well from the Chris. However, I would like to show it once again, and you should really be concentrate on the T0 values. As Chris told, this is a nature rubber has the lowest T0, and with styrene butadiene rubber has a slightly higher, and the highest has a butadiene rubber. We can see it here from this work from Lake and Yek from that 78. Yeah, and butadiene almost about 100. So that is what we did as well, and Chris introduced it even in his presentation. We repeated this analysis and determined with our intrinsic strength analyzer the T0 values, and they are very close to that what Lake and Yech published in this history, let's say. So, and the same ranking, the largest has a butadiene rubber, the lowest nature rubber, and in between is the styrene butadiene rubber. Okay, let's go to the transient point. It is really important to understand each point within this crack growth, fatigue crack growth characteristic. So the transient tearing energy, what is it, this point? Let's say it can be understood as a discontinuity of the fatigue crack growth curve. However, let's say, can in some nature problem be a discontinuity? That's a big question. And let's say I never saw within a pristine rubber such a transient point in all I measured in the past. What we did once is what was presented from a colleague, Mr. Ghosh, Dr. Ghosh, and in 2014 we published a paper where we investigated blends. This was a blends, NRBR, in a portion pure NR, and then was NRBR 80-20, 70-30, 60-40. And let's say if we will really focus in a detail, we will see mostly that NRBR 100, pure NR, there is really more or less no transient point. However, once we are really the BR content will increase and we will incorporate it there, then the transient point will be more dominant with an increasing BR content. So let's say, from my opinion, for example, such a transient point can be associated with such an effect like fracture mechanic in a blends. Yeah, some interface between two rubbers. However, in a pristine rubber, there is more or less any transient point. This is important to understand and maybe to investigate. So then we have a phase 3, which is a stable crack growth described with power law. And again, some data or some diagram investigation of 3 different material, again from Mr. Ghosh, from the second book, where Mr. Ghosh nicely presented even as well a lot of influences on a fatigue regrowth characteristic. And this is these are results for pure nature rubber, styrene butadiene rubber, and butadiene rubber. And as you can see, that's nicely correspond with that what Chris presented within the first presentation. Exactly, we have the largest resistance against fatigue regrowth in a nature rubber. And the weakest material is the butadiene rubber, and someone in between is a styrene butadiene rubber. Very exactly corresponding, and as you can see, within using a different machine, there is always the same result for these materials, corresponding even with the Lakenyak. And then we have the last point, which is the TC, and what we can see, what we measured as well with another method, is that nature rubber has the highest TC, then it is an styrene butadiene rubber corresponding again with the Lakenyak, and the lowest TC has the butadiene rubber, as exactly expected from all of you. So this nicely correspond, and really we can everything find about the rubber fracture behavior within this diagram. So, and now fatigue can grow in a praxis. This was slightly the theory, how approved with laboratory method. And what is in the practice? In the practice, we have here some example of tyre, and in a tyre, or here, we can find, let's say, every fracture processes we have there. So there is a wear, fatigue wear or abrasive wear. We have fatigue regrow visible here. We have cut and chip here. And how this is associated with that fatigue regrowth characteristic we have here. So we will find here for that lower tearing energy region, the wear, firstly the fatigue, and then followed by abrasive wear. Then we have a fatigue regrowth, and finally we will find a cut and chip. This was even nicely presented from Dr. Ghosh in the previous presentation. However, we can really everything find there in this diagram. This is a very powerful diagram, and we need to understand it. And if we will follow some really these basic polymers and focus only on polymers like a nature rubber and butadiene rubber, then we really can very clearly see, for example, that with increasing of nature rubber, this is for this low tearing energy region, that higher resistance against crack initiation and abrasion or wear will be achieved. In the middle part for stable crack low, that's mean that for a lower fatigue crack growth rate, NR deliver a higher resistance against fatigue crack growth. And even for TC, that's mean cut and chip behavior, for example, for the real application in a tire, that's mean we need to use nature rubber compared to butadiene rubber, while nature rubber due to strain-induced crystallization will cover really the highest resistance against such a cutting process. That's been very quick crack growth processes. And compared to butadiene rubber, once there will be some crack propagation, it will immediately propagate close to TC, and we will never be able to stop it. So, importance of fatigue crack growth behavior. So, there we can summarize it like that. The knowledge of fatigue regrowth propagation is too important not to be described accurately. Accurate numerical predictions require absolutely precise data. Each change in the fatigue regrowth curve represents a change in fracture behavior, whether in fatigue or abrasive wear, fatigue regrowth, or unstable crack propagation. So each change is a manifestation of a real change in rubber behavior. And therefore, the main question is, how is it possible to determine the fatigue regrowth characteristic absolutely accurately and, let's say, addition completely from the T0 up to TC, and once again, accurately as much as possible. So, okay, so how to do it? Exact determination of fatigue regrowth. We have here that example, which Chris presented as well. This is an EPDM with fill fraction 0.24. What we did was we performed a very detailed fatigue regrowth analysis with our tyre and fatigue analyzer. So very detailed to have really as much exact curve as possible. The all phases we performed and going over. So and now there is a detail of these three phases. Of course, we avoid the first phases and we start with the second one, starting with T0. This is this diagram. Then in the middle we have the stable crack growth, the parallel phase, and then the last one is the close to TC up to TC, of course. What we can see here with the black point are the experiments, and with the blue points there are an let's say approximation with a from our side defined specific function for each region. That means we define, and you can see it here in the blue rectangle. We define three different specific functions for each phase we have here. So for the second, third, and fourth, yeah, these are some parameters for the functions, and here we can see the sum of square of deviations, yeah, are 2. So you can see that we are 0.998 for the second phase, 0.9956 for the third, and 0.9996 for the last one. So what we wanted to see here, we wanted to see, is it enough to use a power law, or there is a need for to use another specific function. And what we see is, in general, for this material, which is EPDM, where the crack growth are really propagating really very nicely, and there is a very stable crack propagation, which would not be the case of nature rubber and another one. However, we use this to get really a very precise data, the EPDM. We can see that for the compare, let's say now for the third phase, stable crack growth, we see here this line is the power law, and the power law has the sum of square of deviation 0.992. With the another with our defined specific function, we are at 0.9956. So let's say it's for sure better. However, even 0.992 is a great results. However, let's say what we need to say is for this material it's okay. We can be much more precisely than a power law, and what we are expecting is with another polymers like nature rubber there will be a larger difference, maybe. Yeah, we need to investigate. However, to use the specific functions make a sense for to getting precise data. What we did here now is we did this stable crack growth for two different material. This is a two different filler fraction. The first one, the left one, we know already, and the right one, there is a larger filler fraction, 0.29. What we can see here there is a larger difference between the power law and our specific function. Power law gives the sum of square of deviations 0.97, and with our specific function, identical for the both of them, yeah, what we did previously, what I presented previously, is 0.9995. So fast identical behavior, and you can see on the shape, it is really important to follow exactly the shape of the behavior. It is not exact power law. If we would like to have exact data, we need to have a specific function. Okay, now very important question is the time requirement for the fatigue regrowth determination. You can see here for this EPDM fill fraction 0.24, there is a right-hand side diagram, which is the dependent steering energy on a cycle number. How many cycles we needed for the measurement of this steering energy of the crack propagation. There are two data sets, A and B, whereas the A is currently applied time, that means what we really applied, and that B is recalculated time to reach the crack growth 0.01 millimeter, 10 microns, because 10 microns would be enough for the optical system of the tyre and fatigue analyzer to detect there is a stable crack growth. So, and what you can see is that, let's say, only for the B parameter, for the B measurement, we need for the evaluation of the phase 2 close to T0, we need approximately 3,000 hours of a measurement. Whereas for the stable crack growth, the phase 3, we need only 19 hours. And for the 4, close to the ultimate strength, critical tearing energy, we need 0.005 hours to have it. So that's very important information, because this is really too slow. You need a lot of time to make such an investigation. This is, let's say, yeah, okay, optimal. We can do it very quickly. And this is too fast. Yeah, we need a very, very accurate system to get such a data on a precise, very precise way. So these two, the phase 2 and phase 4, would need some, let's say, improvement to get it accurately. And in a phase 3, we know that we need, let's say, to measure as it is, however, we need to more precisely define the specific function compared to power law. So how to proceed more efficiently to determine complex fatigue regrowth behavior in minimal time with highest accuracy? Let's say, yeah, there is a possibility, as Chris introduced. These 2 points, T0 and TC, these can be very quickly, within 1 to 2 hours, determined with that intrinsic strength analyzer. So we would have these 2 points. This middle part, there is a, yeah, let's say, very okay time to analyze it, and very efficiently to analyze, and very accurately to analyze with tyre and fatigue analyzer. That's very common, and that is the best choice to do it. So this is a stable crack growth determination within few hours. So generally, within few hours, we can have T0, TC, and a stable crack growth. And of course, the question is how we could get these parts to have exact, complete fatigue crack growth curve. This is what we would need to have. So a novel approach for the determination of fatigue crack growth is, let's say, finding a general function defining, let's say, the fatigue crack growth rate in dependence on tearing energy. One function which would describe this complete behavior. How to do it? Let's say we have that function already. However, I will not introduce because this is not the part of the book, and I will introduce them later in the future. So we have here, yeah, two. Yeah, I will do it like that. So sorry. One back. We can, with this intrinsic strength analyzer on a well-known curve we have already, we can define everything. So if we will have another material like this EPDM with fill fraction 0.29, this is the black one, we can this determined with tyre and fatigue analyzer, this stable crack growth. And then with intrinsic strength analyzer, we can determine these 2 points for the EPDM. And that's mean if we have that now we have that parametrical function for the first material. We can change the parameters, fill it with the data we have already done with that ISA and tyre and fatigue analyzer, and then to make the complete function as it is. And that is what we need to do. The complex fatigue crack growth behavior exactly can be determined in a minimal time requirement with using these 2 equipments, and we can have a very exact, complete fatigue crack growth curve. So let's say ISA and TFA are very powerful set of equipment for highly efficient determination of exact fatigue crack growth data, as we see, with connection as well with the one function for the description of a complete fatigue crack growth. And one point more is how to, let's say, use the right spaceman's geometry to understand that we have the right data. I will go very quickly to this presentation, to this part. So in general, as you see, we are using a plane strain, which is so-called pure shear sample. And this is very important, the pure shear. I suppose everybody know from you, what does it mean? It doesn't mean only that we doesn't have any deformation orthogonally to the main strain, let's say in the direction of the width of the sample. There is no deformation. This means pure shear. However, I am not calling that pure shear. I am calling plane strain, and you will see why. So the plane strain is a let's say optimal sample for the crack growth characteristic or measurement, because within the pure shear region, the crack growth is independent on the crack length, and that's mean we need to ask, what is the size of the pure shear region within the plane strain sample? And is there any pure shear region? These are the main questions. So within the next paper we presented with a colleague in the book, we investigated this phenomena on the different aspect ratio. That's mean the aspect ratio width to length or height of the sample from a 0.5 up to 10. And we used digit image correlation to describe really the deformation fields or strain fields in the x direction, let's mean in the direction of the width. So what you can see in a first point, a first step, strain influence. If there is a strain influence on the deformation, on a strain in this direction. If you see such a diagram for different strains, you will say, yeah, maybe there is an influence. However, then I will show you something. I will normalize now this diagram. And what I will get for all strains from 0.05 up to 0.5, 50%, there is no difference. We have in the x-axis, that's mean that is the abscissa, and on the y-axis is a constant contraction. If we have a contraction, let's say from this point up to this point, how big is the contraction? That's mean the deformation. And you can see from that 0 point, from the SC, there is always a deformation in this direction. And you can see that, of course, the largest deformation is that SA here. Yeah, that's expectable. However, what is not expectable is that there is always a deformation over the complete width of the sample, independent on the strain. Even you will apply a very low strain, immediately you have there deformation. So we defined a parametrical function, which is quite complicated from a lot of data sets. However, what is very important, what we define for this parametrical function, what is the results of or describes the parametrical function? It's described pure shear region, the width of the pure shear region. However, how big can be the pure shear region when I told you there is no pure shear region. There is a one parameter, which is d deviation, which is in this equation. And this deviation parameter describes what we allow, how big can be the deviation from the pure shear region. For example, as I denoted now here, the deviation, if we allow 20% of a deviation, then we will have here the 20%, and we can calculate how big will be the pure shear region with this point, and so on. And that's a very important point. Optimal spacement geometry for fatigue crack group analysis is the plane strain sample, for sure. But with the knowledge that there is no pure shear state in the sample, and you only can measure this with the knowledge that you know how big is your deviation, how large is your deviation from this pure shear state. Yeah? And that's a very important point. Okay, I'm on the end of my presentation, and I only would like to show you special testing know-how which we have. We did over last years a lot of developments. What about I would speak hopefully, and my colleagues in the future presentation, future webinars, which is, for example, heat build-up analyzer, which is measurement of heat build-up in situ under cyclic loading condition inside of the rubber sample. That's very important. And very fresh testing method and equipment is, let's say, DMTA, which is dedicated dynamic mechanical thermal analyzer, which we are using for accelerated measurement of aging behavior of material related to fracture mechanics. So, and here I am on the end of my presentation. Thank you for your kind attention and for attending our webinar. And if you have a question, then please write it into the chat and I will try to answer them.